So let's start with this circle. It has center O, point X, and we define the power of point X with respect to this circle W as XO squared minus R squared. Those are just the basics. We could also have two circles, W1 and W2, and we're going to define a new function, the power of X, with respect to both circle W1 and circle W2. It's defined as the power of X with respect to W1 minus the power with respect to W. This is equal to XO1 squared minus R1 squared. That's the power with respect to W1 minus the power with respect to W2 is XO2 squared minus R2 squared. Or simply XO1 squared minus R1 squared minus XO2 squared plus R2 squared. And our goal is to show that this function is a linear function. This phenomenon is known as linearity of power of a point, and it's often shortened to simply linearity. It occurs on many late Amy problems and some USMO. To prove the phenomenon, we will use 3 points A, B, and C on a line in that order. And without loss of generality, we can assume that AC is equal to 1. Let AB equal T and BC equal 1 minus. We can now use Stewart's theorem on triangle O1AC with Chevian O1B. Recall Stewart's theorem of man plus dad equals bomb plus. Suppose O1A equals A1, O1B equals B1, and O1C equal to C1. Then, by man plus dad equals bomb plus sink, also known as Stewart's theorem, we get that T times 1 minus T times 1 plus B1 squared times 1 equals A1 squared times 1 minus T plus C1 squared. We can also use the Stewart's theorem on triangle O2AC. We can let O2A equal A2, O2B equal B2, and O2C equal C2. Then we get from Stewart's theorem in that triangle an equation similar to the first one, but this time it'll be T times 1 minus T plus B2 squared equals A2 squared times 1 minus T plus C2 squared T. We can now subtract these two equations and some things will cancel out, like T times 1 minus T. Then we have B1 squared minus B2 squared equals A1 squared minus A2 squared times 1 minus T plus C1 squared minus C2 squared times. This is somewhat similar to the formula for the power of a point with respect to two circles. And indeed, if we add minus R1 squared plus R2 squared to both sides, something interesting happens, as B1 squared minus R1 squared plus minus B2 squared plus R2 squared is equal to, we can split the minus R1 squared plus R2 squared into that times 1 minus T plus T. So we can add that here before 1 minus T. We can also add it before T. So that gives us A1 squared minus R1 squared minus A2 squared plus R2 squared times 1 minus T plus C1 squared minus R1 squared minus C2 squared plus R2 squared times. This works because 1 minus T plus T is equal to 1. So basically we have the power of point B with respect to circles W1 and W2 equals 1 minus T times the power of point A with respect to W1 and W2 plus T times the power of point C with respect to W1 and W. Suppose we call these three things f of b, f of a, and f of c respectively. F of b is equal to the power of b with respect to circles W1 and W2, and similarly for the other two. Then f of b is equal to 1 minus t times f of a plus t times f of c. If we do f of b minus f of c, we get that this is equal to 1 minus t f of a plus t minus 1 f of c. And that means f of b minus f of c is just equal to 1 minus t times f of a minus f of c. So that means f of b minus f of c over f of a minus f of c is equal to 1 minus t. However, that's also equal to bc over ac. Because if we go here, bc is equal to 1 minus t and ac is equal to 1. So 1 minus t over 1 is 1 minus t. So f of b minus f of c over f of a minus f of c is equal to bc over ac. That means the function is linear and the proof is complete. Thank you for watching. Please subscribe if you would like to see more videos, and stay tuned for a late Amy geometry problem that uses this Olympiad geometry.